In the previous recording, I developed the mathematical expression for calculating the work done on a point test charge when it moves through the electric field of a point source charge. I chose the point charges for both of them because the math is much simpler for those. We will have occasion to see other fields, other forces, and therefore other expressions for calculating the work. Actually, not the work, something related to it. Why am I being mysterious? We're going to switch our point of view from work to potential energy. In any case, but just to make the transition, make the introduction to the concept simplest, obviously, as always, we start with the simplest possible situation. So we'll stay with the point charge for a while. So once again, I have a positive source charge, call it Q, and then I had a positive test charge, capital Q, and we calculated the work done as it, in this case, as it moved from a position close to the source charge to some position somewhat further away. And this was, I called this, in the previous lecture, I called this distance here I called this distance here r sub 0. I called this distance here r sub f, r final. And then what I said is the difference between them, that distance there, I will call that simply r. This is a somewhat different meaning to what we have used the letter r for in discussions of the electric force and field, but it is related to it, as you'll see as we go along. Okay, and then I said it turned out the calculation for the work done on capital Q is KQQ over R. Slight mistake there. I left something out. There should actually be a negative sign in front of this. The negative sign is not hugely important. It's mostly a matter of convention. It comes, for those of you who've had calculus, it comes from the fact that if I calculate the expression for the work correctly using calculus, then I end up taking an integral of 1 over r squared. And of course, when you do an integral of 1 over r squared, you pick up a factor of -1 when you raise the exponent. So that's where that negative sign comes from. It does have a physical interpretation, but it's not of crucial importance to us right now, so don't worry about it too much. What I do want to say next, though, is in a couple of recordings ago, a couple of lectures ago, I talked about the amount of potential energy the charge had when it was here versus the amount of potential energy the charge had when it was here, and of course those potential energies are different. So now I'm going to make the connection between the work and the potential energy. And the connection is this. At this position, potential energy, which I will use the symbol capital U to represent. Your book, I think, uses capital U sub E or capital U sub ELEC for electric or something. I'm just going to let it be capital U. Okay. The potential energy there is equal to the negative of the work that is involved in getting the charge there. Okay, and this expression is a little misleading. And so let me try to explain this, because it sounds like, well, here's why it's misleading. Work is done only when an object changes position, but potential energy, you can say that an object has potential energy at a single location. So that suggests that this thing here, U, capital U is evaluated at a single position where the work requires two positions. Well, hopefully you remember from your studies of energy in mechanics that in fact the potential energy at a single location is not really evaluated from just a single position, but in fact this here represents the difference in potential energy from wherever your particle happens to be right now from wherever you have defined your potential energy to be zero. So in fact, this is also a potential energy difference between two places. It's just that one of the places here is the place where the potential energy has been defined to be zero. And so if I call it U or I call it delta U, I'll get exactly the same numeric value because all I'm doing is subtracting zero. So really this is a change of potential energy from the place where it is zero to the place where it isn't zero. This work here is the work done in getting it from the place where it's zero to the place where it isn't zero. And even more generally, even if I don't start from where the potential energy is zero, I start somewhere in space and I move to some other place in space, well, then in that case, the way I interpret this is that this is the potential energy difference between how much potential energy it had when it was here versus how much potential energy it had when it was here. So U is actually the change of potential energy from R sub 0 to R sub final. Okay. Technically, we should probably call this delta U, but similarly to something that we did in a previous lecture, as a general rule, we don't put the delta there simply because our equations are going to be complicated looking enough without adding another unnecessary symbol. It's unnecessary as long as you always remember that this is referenced from some place where we call zero, or it's always referenced from some starting point to some ending point. With that understanding, which you always have to keep that in mind, then this equation is okay. So the work that you do in getting the object from R0 to R final, the amount of work that you do results in and causes a change of potential energy of that particle. So here it has a small amount of potential energy. Here it has a large amount of potential energy, or at least larger. So this change of potential energy was positive. Okay. It gained potential. I'm sorry. That's a mistake. I'm sorry. Forget that. I'm sorry. It has a large amount of potential energy here. Has a smaller amount here. And if you're confused by that, as I was just a moment ago, in a couple of recordings ago, my test charge was a negative, and so that reverses where it's a high potential energy and where it's a low potential energy. Right. Okay, so I'm making this more complicated perhaps than it needs to be. Ultimately, my goal is to calculate the expression for the potential energy that the charge has, and the answer is it's simply the negative of the work done. So in this example, where both charges in question are point charges, the potential energy is calculated by Q times K times Q over R. Okay. I trust you noticed that when I wrote this, I wrote it in a peculiar way. I pulled the test charge out of the expression. Why did I do that? Well, you may be able to guess. If you look at the stuff inside the parentheses there, K, of course, is our constant. Q is the source charge. R is the change of position of distances from the source charge. You're this close to this. You're this close to the source charge. Then you're this close to the source charge. So R is our final minus our initial. So these are distances from the source charge. This is the source charge. This is a constant. So in other words, the stuff inside the parentheses, it refers only to the source charge. And if this is starting to sound familiar, that's good, because I made the same kind of approach analysis when I transitioned from electric force to electric field. The electric force on the test charge to the electric field of the, did I say that right? The electric force on the test charge to the electric field of the source charge. Now I'm making the transition from the potential energy of the test charge to something else, which will be a property only of the source charge. So let me write that down. Okay. So since this thing is a property only of the source charge, just as I did with electric fields, I'm going to give it a symbol that is different from, but related to, the symbol for potential energy of the test charge. That symbol is going to be capital V. There's a reason for calling it capital V. It's not a particularly good reason. In fact, it's a terrible reason, but I'll tell you what it is pretty soon. In any case, this thing, as terrible as the reason is for the symbol that we've chosen to give it, even more terrible is the name that we're giving this symbol. And if anybody had been asking me, I wouldn't have given it this name. And so I warn you in advance, the name I'm about to tell you for V here is a terribly, terribly confusing name. And so I warn you now, and I will repeat this many times, you've got to pay attention to what this means, because it's the world's stupidest name. Anyway, it is called the electric potential of the source charge. Electric potential. And the reason that's the world's stupidest name is, of course, because it is terribly, terribly easy to confuse V, the electric potential, with U, which is the electric potential energy. But this is the electric potential of the source charge, whereas this is the potential energy of the test charge. So potential versus potential energy. Source charge versus test charge. Okay? And as a consequence, there's two things. First of all, I can write the expression for calculating the change of potential energy of our test charge in a very simple way. More than that, you'll notice that the mathematically difficult and mathematically interesting stuff is calculating V. Once I know V, which is a property of the source charge, anytime I want to change the potential energy of a test charge that moves around in the vicinity of my source charge, all I have to do is multiply that test charge by V, and I automatically have the potential energy if I want it. So the focus for us from this point forward is going to be primarily on calculating V, and then we'll calculate U whenever we feel like we want to, whenever we get around to it, if we ever do. And again, this should sound familiar. It was exactly the same kind of language I used when I said, having introduced the concept of the electric field, I said that F for 2-point charges is, oops, K times, actually, let me do it like this. Q times K, Q over R squared. Then I defined E as KQ over R squared R hat. And then we could write Coulomb's law in a trivially simple way. All right, so we're following exactly the same path. However, the thing that makes the energy approach useful and powerful and better is that whereas force and the electric field are both vectors, potential energy and therefore potential are both scalars. No directions here, no vector components, none of that stuff. These things are just, they add like numbers. Much easier to work with. That's the reason, and that's the power of the energy approach. Okay? So anything that we can do, virtually anything that we can do with forces and fields, we can do with potentials and potential energies. Sorry, I should say that backwards. Anything we can do with forces and fields, we can do with potential energies and potentials. Okay? And 99% of the time, it's mathematically easier to do it with energy than it is to do with forces and kinematics. Okay? Most of our time is going to be spent calculating potentials, a little bit calculating potential energies. For the record, I'm going to go ahead and finish up the whole conservation of energy thing. So I'll talk briefly about kinetic energy in electrostatics as well. That'll be the next lecture. Having done that and sort of and wrapped your head around that, then as I say, we'll turn our focus primarily to the electric potential of the source charges. So kinetic energy next.